Good morning and good afternoon, everyone. Welcome to Coffee Break webinar series. Today I'll be covering time history replication in SignalCalc 900. My name is Holden Gibbler. I'm an applications engineer for data physics. Today is August 7th. The agenda for today is I'll cover how to set up a time history replicator test. I'll do a brief explanation on recordings and how to splice recordings together, and then we'll just cover some real-time control just to get you started on your systems. Okay, here we have our Manage Tests tab. If you're familiar with our software, you should be familiar with this tab. I can access a new test here by hitting Test New and Replicator. Before that, I want to cover some of our time history recordings, so I'll hit Cancel. If I click Recordings here, I can view all of my different recordings. If I open them up, I can double-click them and view all my different time histories. I can also import time histories from an ASCII file. So maybe in your application, you might have an ASCII table that you want to import and then replay on one of your shakers or replicate on one of your shakers. And I'll show you that in a moment. So the first thing we'll do is we'll make a new test, and I'll call it Coffee Break. To access a replicator, you'll click Controller, go down to Replicator Control, and then you can select the template. Click Create Test. If you're familiar with our software, you should know that the Test tab is just for annotations, and the Channels tab is where we enter our sensitivity values, set our coupling type for all the different input channels. In this case, I'm using a 901. I'll hit Edit System and just make sure my 901 is connected online. I only need one control channel in this case. For the purpose of this demonstration, I have a 901 with a BNC cable connected from the drive channel or channel 6 to my first input channel here. My coupling type set here, fine. I'll click Replicator. So there's a lot to cover in the Replicator tab. First thing I'll cover is the time reference here. So in the beginning, you'll have a default RPL reference, which just comes standard in our software. If I want to open a time history or a throughput file or time history recording, I can hit Open, and then I can double click one of these time history recordings. I can also hit Edit and bring up our time history recording window where we can splice together different time histories to create a sequence. I can add cursors here, and I can see a zoom view between two different min and max bounds. Here's my zoom view, and then this is the FFT or the frequency spectrum of this zoom view here. I can also integrate this throughput file, so I can see velocity and I can see displacement. Something that's important to consider is your lower frequency response on an electrodynamic shaker. Usually have bad performance below 5 Hertz, so it's useful to add a high pass filter. You do like a 3 Hertz high pass or a 10 Hertz high pass filter. This will decrease the displacements. Go back to acceleration. Here we also have test sequences where I can swap between different time minimums and time maximums and choose to play those sections back. I can repeat them. I can scale them down. But what I want to do, what I'm interested in, is editing this current reference. So I'm going to hit Edit, and this will bring up our part of our test setup window where we can map and edit our existing time history. So here's our default RPL reference. If I want to clear it from the bottom menu here, I'll just click Delete. And then it'll say, are you sure you want to confirm? Hit yes. Now we have a fresh reference here. What I can do is I can click my source. I can add cursors here. And I can specify what sections of this recording I want to enter. So maybe I just want to replicate the first 30 seconds of this time history here. So I'll put a cursor between 0 and 30, and I can click Append. And then it'll paste this 30-second time history to my source file here, or from my source file to my reference profile. I can also map to a set channel. So in this case, I want to set to my my control channel on input 1, but a lot of your throughput files will have multiple different input channels that can be the target file or the target source. You want to match these up. If I want to, maybe I want to replay. So I have 0 to 30 seconds. Maybe I want to see the 15 to 45 second mark. And I want to, replay this section. So I can add a cursor here. And I can drag this cursor to the 45 second mark. I can add a cursor down here. And I can choose where I want to insert this section to in my my reference profile here. So what I can do is then I can add linear ramping as well. This is important. So one, it's easier to control, and two, we don't induce any large transient like shocks into your test article. It's easier for the controller one to ramp up and ramp down between each sequence. So what I'll do is I'll add a linear ramp left and right bound. So if I hit insert here, you'll see what that looks like. So now I have, if I can zoom in here, you can see that I have this little ramp that I specified, a linear ramp. So at the end of the sequence, it'll go down to 0 and then ramp back up. I can also see in this first part, I forgot to add a ramp. So I can add a ramp in post-process here. So let's just go to here and let's add the left bound. And I want to do about a half a second ramp so I can look at my DX value. And I want it to be about 0.5. So it looks like about half a second. Then I can go to scaling ramping, and I can add a linear ramp here. And the way this works is we have values from 0 to 1, 0 being the smaller number or the smaller part of the ramp, and then 1 being the larger factor, and we'll add a linear scaling between the two cursors. So if my right side, I want it to be smaller and my left side to be the larger number. So I'll put a 1 here and then add a 0, and then I'll hit apply, and this will add the linear ramp. I can also do it to the front end as well. So I can go all the way over here. Again, I want to add that half a second ramp. So my DX is about half a second here. Instead of my left level being the larger magnitude, I want the right level to be the larger magnitude. So I start out small and ramp up. I'll hit apply. And there we go. So now we have linear ramps applied. I can also add a high pass filter. So again, I want to filter out maybe 5 hertz, all the components below 5 hertz. So I'll hit apply. And there are some changes, but not that much. I can also choose to resample my reference profile as well from my source. Okay, so if I'm happy with that, then I'll go ahead and hit save. And then now it should be inserted here. So now I have my time reference up here, and I can look at my zoom view. So I can see my first section here. Yep, there's my frequency domain. And then now that it's, I applied that 5 hertz high pass filter, you can see the displacements are much better. Okay, and then here's where I can edit my sequences as well. I don't really care to have some of these sequences. So if I want to delete them, I'll highlight them and hit this little minus sign, which will delete the sequence. And if I want to edit the sequence, so right now it looks like it's from 0 to 15 seconds, and I want to divide my reference up. So I have this sequence from 0 to 30 seconds and then 30 to 60 seconds. So I can do that is I can add these cursors here. I can highlight it, then I can see this little button that says update sequence from cursors. I'll go ahead and press that. And then now the Tmin and Tmax will adjust based on the cursors on my graph. I can also add a decibel scaling to the level of the sequence. If I want to start out 6 dB down, I can enter a -6 here, and that's useful for the start of your tests. In this case, I'm running a wire, so I don't really need to worry about that. But on actual test equipment, it's a good idea to add to start out at the lower level. But I'll just add a 0 there for the meantime. I'm going to adjust this second sequence so that my lower bound is at the 30-second mark and my high bound is at the 60-second mark, so I can fully define that second sequence. So again, I'll just hit this little arrow, update. So right now it says from 10 seconds to 30 seconds. I want it to be 30 to 60 seconds, and it just did that. I can also edit the name here. So for this first section, I can say 0 to 30 seconds. And then I can say from 30 seconds to 60 seconds. And then I can rename this entire sequence because it's from 0 to 60. I'll call this full sequence. Okay. And I'll go over some of the parameters here. So the smoothing is, I know we manually added a linear ramp to the front end of each sequence, but by default we can add smoothing here. And for the first block and the last block in the sequence, 50% of the block will be applied. A linear ramp will be applied, and I'm just going to keep that by default here. It's just for safety in our system. Here's our correction factor. So we have a sensitivity value. So essentially what this means is that I have numbers between 0 and 1. The larger the number, the more we'll correct for each frequency line. It's also based on the control parameters here. We have a global one for the all sequences, and its default set to 0.5. What will happen is this number will be multiplied by whatever the sensitivity is here. So usually by default, you can leave it at just 1. So globally, it's always applying a 0.5 correction factor. But in some cases, sometimes maybe you have a troubling part in your sequence here, or in your reference, and you could adjust the sensitivity. So maybe we want it to correct slower. So maybe with this first part, maybe I had some strange behavior, so I want to correct it. I'll do 0.5. And what happens is this number will then multiply by my global correction factor. So then really for the sequence, it'll be 0.25. In this case, I'm just turned to 1 for example's sake. Here we have linear averages. So these are linear averages used in our control FFT computation. Usually by default, you want to leave these at 1, and then exponential averaging, leave it at 8. If you're on a hydraulic shaker, you might want to turn this down to 4 because of the nonlinearity of the system. That way we have a faster response. But everything looks good here. So I'll just move on to the alarms and aborts. So here we have the alarm RMS and abort RMS. Essentially what this means is that at 50% RMS, we'll trigger an alarm in the run log. If we get above 100%, we will abort, or 100% RMS, we will abort the test. We can define it separately for each sequence. We also have a min threshold and a max threshold for GRMS. What's useful too is for here, when I'm ramping down, let's see between my cursors, it's extremely low amplitude, and I don't care to correct because we're just correcting into the noise floor, and I don't want to waste time trying to correct these small amplitudes. So I can add a minimum threshold here. So if the reference RMS level is below this level, RMS aborts will not be enforced. And then once they exceed 0.3 GRMS, then I'll turn back on my abort tolerances. This just allows us to not waste time correcting for like what are lulls in your time history reference. So sometimes maybe you're trying to replicate some shocks or whatnot, and there's a lot of downtime between events. This will just allow you to not apply control for those smaller, or apply abort limits for those smaller events. I can add a time domain tolerance in here as well, and an error exceeds and error repeats. If I want to loosen my my errors, I can add more exceeds or more repeats. So if I have 1 exceedance here and then 1 repeat, the test will abort. But maybe I want it to be a little more loose, and I can add 2 or 3 error repeats before the test aborts. Okay. Let me go to control parameters here. So if you're familiar with our system, you usually use autofill from reference, but if I uncheck this, I can adjust the block size and adjust the frequency bandwidth. Usually I just recommend using autofill from reference. I'm going to skip my stop switch because I don't have a stop switch connected. My strategy here, we have store drive in real time. And this purpose of this demonstration, we'll just cover real time control, just easy to get started on your shaker system. Mode, we'll use test mode. We can also use iteration, but we're going to cover test in this case. This is our min frequency cutoff. I set this 5, but usually 10 is a good default. If you do have some low frequency components, you should turn this down to about 5 hertz. Here's my global correction factor. Higher this number, the faster I'll correct each frequency line. The lower it is, means no correction. Min change. So essentially what this parameter means is that if between blocks, if my private frequency line that changes less than 1% from the previous block, I won't apply any correction. The min frequency amplitude. So sometimes, especially in time histories, you're replicating a real event. You won't necessarily have energy at certain frequency bands. So let's say I had no energy between like 100 and 150 hertz. I won't bother to apply amplitude correction for my everything under 10% of the frequency amplitude. So again, with that, if I go back to my reference for times where the amplitude is extremely small, I won't apply amplitude correction because it's not needed. The max change, usually it's recommended to keep this at about 100%. This allows to prevent overcorrection. Instead of 250%, so we can correct between blocks. We can apply a 2.5 times max change for each frequency line. Pretest, here we have our pretest parameters. We have a coffee break seminar series that covers the pretest in depth. Highly recommended on our YouTube channel if you want more information on that. Again, last thing we'll cover is our run schedule. So I won't need these sequences here because I have nothing defined, so I'll just delete them using the minus sign. And then maybe for this, I can add a little loop here. So I'll add a little do loop, and then I'll add a loop, and I can specify the number of loops. So what will happen here is that I will run sequence 1, which will run 0 to 30 seconds, and then I will jump to sequence 2, and I can jump to my full sequence and run the entire reference again. I can also change the order of these. So maybe I want to run sequence 2 and then sequence 1. You can do that. You define a sequence here. I can change the save rate here. So I can save every sequence, or maybe I don't care about saving the full sequence as much because I'm saving these 2 sequences. So maybe I can just I can set this to 3. So every 3 repeats will add a save here. So essentially in this loop, I'll loop this 3 times, and then on the last loop, I'll create a save for my full sequence. I can also check down here to save the last 30 seconds of my test. This is useful to figure out how the test ended. Okay, I'll go ahead and hit save. And if I want to open up the test, I will double click it. Yes. And then I will hit initialize. And the first thing that will happen here is I'll get an error. This is okay. It's just telling me that my 901 does not have my reference throughput file saved on the unit. So I want to upload it to the controller. So I'll hit yes. It'll upload time history. Okay, it's completed. I'll hit initialize again. Clean that up. Continue. All right, and then we'll start our pretest if I hit start. And this pretest will look strange because I'm running on a wire, so it'll look perfectly linear or near perfect. Okay, my pretest prints a pass. My max voltage is well within my limits. Look at my control transfer function. Everything looks good. I'm going to hit start test, and it'll jump to the control plot. Here I have my control and reference. As you can see, they're nearly perfectly linear. You can hardly see I believe that's green. My Here is the time domain data from the response. Here's the drive voltage here in the time domain, drive voltage and frequency domain. Here's my error. Again, we're at the nano level. We're perfectly linear nearly. There's hardly any error. And then here's my error in my time domain. It's very, very small. Okay, I can add manual saves here as well. But for the purposes of the demonstration, I'll go ahead and stop this. And I'll hit end. And then I'm transferring the save to my computer. And then I want to open and review. I can jump to I have a special review tab made, which will show the full time history. So I only ran for about 8 seconds, but I have everything here. It shows the last block of the control and reference lines, my error, and then my drive voltage. Okay. If you want more information, please visit our YouTube channel. We have more videos that cover a variety of topics. Again, if you want more information on the pretest, you can go there. Thank you again. My name is Holden Gibler. I'm an applications engineer for data physics. I cover instrument products. My email is below. And for more information about our products, please visit our website at dataphysics.com. Thank you.